right, we're back. Like I said in my emails, I'll be recording my lectures from now on and uploading them to YouTube. What I found works best is recording here at home on my whiteboard, and then taking my laptop to work to upload. So beyond the lectures, you have your homeworks on my math lab as usual. Those won't change, although as we go, there may be a few topics where we aren't able to cover it to the degree that I would like to, so I will be informing you of those topics. I can't edit the homeworks at this point, but I will tell you which problems you can basically ignore as we go. I'm still working out the details on what I want to do for exams, like I've explained. Probably for this class, I'll be able to put something together on sorry, excuse me, excuse me. Probably for this class, I'll be able to put something together for exams on my math lab, but we have plenty of time before I have to worry about that. But there shouldn't be any reason for you to have to come up to the campus for classes or tests at this point. Our priority is to get through the semester without having to have any unnecessary campus visits. And then as I go through my lectures, if you have questions over things that I talk about, you can either send me an email with your questions, or if you have a YouTube account, you can post questions in the comments. And if they're simple questions or questions that I'm able to answer through text, I can reply with the answers. Otherwise, one possibility is as I get more and more questions, I can make extra videos that answer student questions. I'm also looking into the possibility of having office hours through Zoom, to where you could video conference with me with your questions. I'm still not sure how that'll work, but I'll let you know as I figure things out. All right, so this is elementary calculus. I'm going to try to keep these videos in the ballpark of 40 to 50 minutes to make them more manageable. So we'll think of them as each one is approximately one lecture worth. My goal, let me double check something. My goal for the remainder of the semester is we basically have to get through most of chapter 4. We've already finished 4.2, so we have a few more sections of chapter 4, and then there are just a handful of sections from chapter 5 and chapter 6 that we're supposed to talk about. So that's the plan. Okay, so let's first review what we were talking about before the break. We had talked about integrals. And we had the basic integral, the indefinite integral, which is the integral symbol of a function little f of x, and we say it's equal to another function capital F of x. Let me emphasize that this is a capital F here. Capital F of x plus c. This means capital F prime of x equals little f of x. So an integral symbol, this integral symbol is like the opposite of a derivative. So in words, capital F of x is an antiderivative of little f of x. All right, so with that plus c there, so to remind you what that is, the plus c is a constant. That the c is a constant. It's an arbitrary constant. And so the point is, if I take the derivative of this, the derivative of a constant is 0. So that plus c does not affect the derivative. So if I take the derivative, I get back this original function, little f of x. So this, let me rewrite this. This is what it means. I'll remind you of some simple examples in a second, but just the terminology that we had. This thing here was, we had a couple words for it. It's the indefinite integral of f of x. Or another word for that, or another terminology for that was the general antiderivative. Of little f of x. So capital F is any antiderivative. What makes it the general antiderivative in this case is that plus c, plus that arbitrary constant. Okay, so then we had several rules for antiderivatives. I'm not going to repeat those here. Hopefully you have those in your notes. But we had that on the last test. But just to remind you, since it's been a while, when we take the antiderivative of, let's say 9x to the fourth, so integral of 9x to the fourth dx. This is a power function, but the way it works is if we've got a coefficient already, we keep that same coefficient and then take the antiderivative of x to the fourth. So this is the opposite power rule from derivatives. The derivative of a power function would be we bring that power down and multiply by it and then subtract 1 from the exponent. When we're doing the opposite, the antiderivative, that exponent needs to get bigger, so we increase the exponent by 1, so that's now x to the fifth, and then we have to divide by that new exponent, or multiply by 1 over that exponent. So 1/5 x to the fifth, and then we tack on our plus c. And so our answer to this problem would basically be a function, the 9/5 x to the fifth plus c. All right, so like I said, we had lots of these rules, and we did lots of practice with different functions to take the indefinite integral. And then what we talked about lastly before we got to the test was section 4.2. This is just a very brief reminder what it was. I'm not gonna go through all the details again. But 4.2 was, I can't remember what it's called, integrals as areas, or antiderivatives as areas. And when f of x was a positive function, then it has a graph that looks something like this. And if we look at the region underneath the graph between two x values, a and b, then our notation, integral of f of x from a to b, so it's the same symbol, but now we put these x values on the integral symbol. Let me use a different color here. What this represents is the area underneath the curve and between these two x values. So if I shade this area, hopefully that shows up somewhat. Then this integral from a to b is the area under this curve. So it's this shaded area here. All right, so the last time we had actual new material in a lecture, we were talking about how you actually calculate this by chopping up this interval from a to b into smaller pieces and then approximating this region with rectangles. So we did a little bit of that, but the point I left it with before we switched to reviewing for the test was actually doing that for concrete functions is difficult. It takes a lot of work and it's tedious, and it's very difficult to generalize for arbitrary types of functions. All right, but the other thing I should mention before I erase all of this is, I don't want to, the terminology here, again, it's still an integral. It's the integral of f of x dx from a to b. This is called the definite integral of f of x. So without the numbers, it's indefinite. With the numbers, it's definite. All right. So moving on, we want to talk about what is a good way or an easier way of computing the value of this. So the other point I want to reemphasize is this type of integral, the answer will be a number. So there won't be any x values or any other variables. The answer to this integral will be a number, a numerical value. All right, so section 4.3 then is how to compute these. I can't remember what the actual section's called. Definite integrals, I guess. Okay, so we start with the major fact here. This is called the fundamental theorem of calculus. And what it says is it makes the connection between the two types of integrals, indefinite and definite integrals, essentially. So what it says is, if capital F of x is any antiderivative of little f of x, then the integral from a to b of little f of x is computed by taking this antiderivative, capital F, and plugging in the bigger of the two numbers, or the number at the top of this integral symbol, b in this case, and then subtracting capital F of the lower number. Now, I find it's helpful to, instead of writing this, to write it like this. I'll explain. Capital F of x, and then I put this bracket symbol. Some places you'll see just like a longer vertical line here. At the bottom, we'd say put A, and at the top put B. What this notation means is you have the function capital F of x, you plug in the top number first, like we did here, and we subtract the function with the bottom number plugged in. So f of x, capital F of x, evaluated at b and at a, understanding that you're subtracting the two values. Okay, so let me do a couple examples first. We will worry about why this is true in later. But let's first do some examples to make sure we understand exactly how to use this, because the most important thing is understanding how to use this fact. Okay, so let's evaluate the integral of x squared dx from 1 to 2. All right, so the way I think of this is basically a two-step process. The first step is take an antiderivative, or take the antiderivative, so of our function x squared. That is again a power function, so we increase the exponent to make it x cubed, and then divide by 3. Divide by the new exponent. So 1/3 x cubed. And make sure I should be careful with how I write this, because my handwriting's not as good on the whiteboard. A big mistake I was seeing on some of the test questions was when you are taking the antiderivative, the x part is not put in the denominator unless it has a negative exponent you're dealing with. The x part is separate. The fraction is the coefficient. So the divided by 3 is not right next to the x cubed. It's 1/3 times x cubed, or x cubed divided by 3. All right, so we take that antiderivative. We don't need to worry about the plus c, because if you go back to the stuff I just erased, all we need is any antiderivative. We don't need the general antiderivative, just any specific antiderivative. So the plus c is unnecessarily complicated. Just get that first antiderivative, and that's all you need. Then we're going to plug in our two x values, 2 and 1. So this integral equals this antiderivative evaluated at 2 and 1. So I'm going to have 1/3 times 2 cubed minus 1/3 times 1 cubed. And so then we simplify that. 2 cubed is 8, so this is 8/3. 1 cubed is 1, so this is 1/3. So 8/3 minus 1/3 is 7/3. And so that's our answer. So the picture, x squared is just our parabola, or some parabola like this. And my scale's probably off, no doubt, but if I look between 1 and 2, and look underneath this parabola between 1 and 2, that region would have area 7/3. The area of that shaded region would be 7/3. All right, let's do another one. E to the 2x dx. Difficult to see how legible this is on the video because it's all reversed what I'm looking at here. But the integral of e to the 2x between 3 and 6. All right, so this is a two-part process. The first part is just like an antiderivative problem that we were doing before. I need to look at this function and go back to our rules and figure out what is this antiderivative. Well, e to the x. So the function e to the x, we have to know is its own derivative and therefore its own antiderivative. So if it's e to the 2x, it's almost the same. I'd write that same function, but now remember, if I were to take the derivative of e to the 2x, I would get e to the 2x, but then by the chain rule, I have this inside function I'd have to multiply by its derivative, which would be a 2. So the derivative of this would be 2 e to the 2x. Therefore, the corresponding antiderivative rule, we have to compensate for that 2 by dividing by 2. If I put a 1/2 in front of it and take the derivative, when I multiply by this extra 2, it'll cancel the 1/2 that's already there. So that's our antiderivative function, 1/2 e to the 2x. Then we've got our two x values to plug in. And we have 1/2 e to the 2 times 6 power minus 1/2 e to the 2 times 3 power. And let me just remind you, once you get to this stage, once you're plugging in x values, there should not be any x's left over. You should just get some computation involving numbers. If there are e's involved, then most of the time it's better to leave the e's unless it's something that you can easily simplify, rather than typing it into a calculator and getting a decimal. So in this case, you'd have 1/2 e to the 12 minus 1/2 e to the 6. Okay. So again, depending on the context of what you're trying to do, this is the exact answer. If I care about interpretations, like if this is an application problem, maybe I want to know what is this as a decimal, in which case I have to use a calculator and type this all in. Let me do that just to give you something to check your calculator abilities against. So this should be approximately 81,175.68. Let's round it off, but it's a number is the point. Okay, let's do one more of these basic examples before I introduce any other concepts. Or let's do a couple examples. All right, suppose we have the integral of 4 square root x dx from 0 to, we'll say 4. All right, so when we're dealing with roots, square roots, cube roots, fifth roots, whatever, these are actually power functions. So let's first rewrite this as a power function. Square root x is the same thing as x to the 1/2 power. A root is a denominator exponent. So square root is 2, so 1/2. Cube root is 1/3. Fourth root is 1/4, and so on. Okay, so once we convert it to a power function, then we can take the antiderivative. Let me deal with the x part first. Our power rule for antiderivatives is you add 1 to the exponent. So if I add 1 to 1/2, that's 3/2. So 1/2 plus 2/2 is 3/2. Then I need to divide by that new exponent. Well, if I divide by a fraction, if I divide by 3/2, it's the same thing as multiplying by the reciprocal, which is 2/3. Okay, then I already have this 4, so I have a 4 in front. Now here, again, my principle when I talk about whether or not to simplify something, simplifying is good if you have to do more stuff with the expression. So in this case, we want to plug some numbers in. So it's probably good if I do a little bit of simplification. There's not much here, I guess, but 4 times 2/3 is 8/3. And let me say this. I'm going to plug in these numbers to this function. This is just review for how do you compute fractional exponents. Well, there's two ways. You have a denominator and a numerator. The denominator is a root. So this is a square root. And so I want to take the square root of x, but then I still have that 3 there. So once I take the square root of x, I then cube it. You can also type it in your calculator, but just to remind you what these fractional exponents mean. You're taking a root and then you're raising to an exponent. Now you can also do the exponent first and then take the root, but it's usually easier to do it this way because that way you're dealing with a smaller number before you, when you're taking the root, as opposed to using the exponent first would give you a large number that you have to would give you a large number that you would then have to take the root of. All right, so we've got square root of 4 cubed minus 8/3 square root of 0 cubed. Square root of 4 is 2, so that's 2 cubed. 0, square root of 0 is 0, so this is all going to be 0 here. So all I'm going to get is 2 cubed, which is 8, and then I'm all right. I copied the problem different from what was in my notes. All right, so try to edit this out if I remember to. So 2 cubed is 8. 8 times 8 gives us 64 over 3. So there's our answer. All right. Let me do one more example to make a minor point. And then with the remaining time, we'll talk about some conceptual issues. X cubed minus 4x plus 3 dx. So there's our function. Let's integrate. I want to keep my numbers relatively small, so let's go from 0 to 1. Okay, so as we talked about with the other integrals, the indefinite integrals, integrating when there are multiple terms, so addition or subtraction, we just go term by term to do the antiderivative. So my first step is to anti-differentiate this. X cubed becomes x to the 4th over 4 minus x becomes x squared over 2. So we have 4 over 2 times x squared. And then the antiderivative of a number 3, you multiply by an x. You introduce an x into it. So 3 becomes 3x. Okay, so because I'm pressed for space here, let me do my simplification just by erasing here. 4 over 2 is 2, so let me change that. All right. Yeah, so this didn't really make my point, but that's okay. So with these, now we're going to plug in these numbers. When there are multiple terms, and there's subtraction especially, you have to be very careful about your signs. So let me write this out carefully. First, I plug 1 into this entire function. So I'd have 1/4 times 1 to the 4th power minus 2 times 1 squared plus 3 times 1. Okay, so I should put all that in parentheses. Then I have minus, and now I open up a second set of parentheses, and I'm going to plug in the bottom number into this whole function here inside this second set of parentheses. Now in this case, when I plug in 0, all this is going to become 0. But just for emphasis, let me write this out. And so you just want to be careful that when there are these multiple term antiderivatives, when you subtract, that subtraction symbol has to be attached to this entire thing. It's a common mistake to leave off these parentheses and just subtract this part and then not apply that minus sign to the rest of it. Right? But in this case, when x is 0 in this second part here, all these terms are 0, so it's just going to be this part here. So we'll get 1/4 minus 2 plus 3 So that is 1 plus a fourth, so that's 5 over 4 if I simplify it. Right. So we're at approximately 30 minutes in the video, unless I edit out some of my babbling. All right, so let's talk about a couple things here. Okay, so the first question is, again, we have this powerful theorem, the fundamental theorem of calculus. I want to at least address conceptually why it's true or where it comes from. Okay, so this is not going to be a rigorous proof, but I want to give you a sense of why this is true, why this works the way it does. So this is, oops, what that? Graph first. Okay, so suppose I have a function. This is y equals f of x. This is my curve. Board's going to fall on me, I feel like. All right, so I have this curve. And now what I want to do is introduce another function where if I go to a specific x value, let me just call it x here on the x-axis, what I want is the area underneath the curve will start from 0. It doesn't really matter where I start, but start from 0 and go to x. All right, so okay, so let me call this red shaded area capital A of x. All right, so then I want to relate this to the definite integral of f. Okay. This will get tricky having to change my picture here, but this is the function. So what a of x is starting at 0. I pick an x and I go out to that x value on the x-axis and I look at the entire area underneath the curve between those two places. Okay, so that's similar to the definition of the integral of f of x from a to b. That would be, let me adapt my picture now. That would be picking two specific x values, b and a, and just looking at the area between those two. Okay, so that shaded region, that's what's represented by this integral. Okay, but I want to relate this to that area function a of x that I just erased. Well, the way I could compute this would be to take the entire area from 0 to b and then subtract the area from a to b. Sorry, from 0 to a. So take this whole area and then subtract this area. So in that respect, this would be capital A of b. That would be the area from 0 to b minus the area from 0 to a. That would be a of little a. Should use a different letter, I guess. Okay. So far I haven't really done anything. I've just kind of reinterpreted this area definition. But now let's ask the question, what is the derivative of this capital A function. Okay, because this what I've written here looks like the fundamental theorem of calculus, except instead of using an antiderivative of f, I use this area function A. Okay, but what I want to argue is capital A is an antiderivative of this little f. Okay, let me write that before I erase. I meant before I erase this. So you want to say capital A of x is an antiderivative of little f of x. Okay. Then if I can argue this successfully, if I can convince you of this, then this equation I've written here is almost exactly the fundamental theorem of calculus. Okay. Then I would just need to argue that once it works for this antiderivative, it works with any antiderivative. Okay. So the question is, why is this true? Well, let me draw my picture again. This is y equals f of x. If I go out to x, then a of x is this region here. I want to ask, what is a prime? Or what is the derivative of a? What is a prime of x? This is going to be a little bit abstract. I just want to make a brief argument though. So what is a derivative in general? A derivative is a rate of change. How much a function changes if I change x by a tiny bit as that tiny change in x goes to 0. So it's the rate of change of the instantaneous rate of change of my a of x in this case. So let's think what would happen if I increase x by a little bit. So I'm going to move out to a little bit farther. I'm going to exaggerate here. If I go a little bit farther, I'm going to get some extra area here. Let me alter my curve a little bit so it's more apparent what I'm doing. So if I change x by a little bit, then I'm going to get a little bit of extra area here. And that's how much a of x would change. That would be my delta a, the change in a. But I want to think of this in terms of differentials, something we've talked about a little bit a while back. Well, this change in x would be called dx. The amount I increase x by would be called dx. Then the amount that a changes is called delta a. I want to approximate it though. I don't want to have the exact change in a. I want to have the approximate change in a. So I'm going to approximate that with a rectangle that meets the curve at this left endpoint here. Okay, so that approximated change in a, that's what we would call dA. That's how much that we expect a to change when we change x by dx. Well, dA would equal the width of this rectangle times the height of this rectangle. Well, the width is dx. The height would be the y value at this point where the rectangle hits the curve. Well, that's going to be f of x. If this is x, this y value is f of x. So dA is f of x dx. But dividing both sides by dx, we get dA over dx is f of x. Right? So dA over dx, that's just another name for a prime of x. So therefore, a prime of x is f of x. Right? So let me just say one more thing about this, and then we'll wrap up this video, and I'll start another video to do more topics. So at this point, we've argued now that this area function is an antiderivative for little f of x, and our definite integral of f can be computed by subtracting a of one value minus a of another value. But I can't really, that much doesn't really help me. I can't really get my head around how to calculate a of x without knowing how to calculate areas, which requires me to do these integrals. So the next step is really the key one. So now we have to reach back to where we first talked about antiderivatives. If capital F of x is any antiderivative of little f, when we talked about general antiderivatives at the beginning of this chapter, so 4.1, however many weeks ago that was now, the point of a general antiderivative was, once we find one, we basically find every antiderivative by adding this plus c. So if capital F is any antiderivative of f of x, then a specific antiderivative, like a of x, is equal to capital F of x plus c for some constant c. So we can say our integral of f of x from a to b, well, as we argued with before from my pictures, this is capital A of b minus capital A of little a. If I replace these a functions with f of x plus c, this becomes capital F of b plus c minus capital F of a plus c. And then this plus c minus this plus c, those c's just cancel. I get f of b minus f of a. So that's my fundamental theorem of calculus. I can use any antiderivative to compute this integral. I just pick my favorite antiderivative, call it capital F. I can take that antiderivative and plug in these two x values to subtract. Okay, so that's all I'll say about why the fundamental theorem of calculus works. If this part of the lecture didn't make as much sense, don't stress out about it. The most important thing here is being able to compute being able to compute a definite integral of a given function. All right, so we'll do more examples of that as we go. All right, so let me stop the video here, and I will start another one to talk about a couple other topics from section 4.1, and then we'll move on. Oh, sorry, not 4.1, 4.3, and then we'll move on to section 4.4.